Hello and welcome. If you are settling in for the evening, finding your position, letting the weight of the day begin to lift, letting the sounds around you soften, then you have come to exactly the right place. This is the Science Channel for Sleep, and tonight we are going somewhere that very few human beings have ever been, and that most of the planet has never seen. We are going down, past the sunlit surface of the ocean, past the twilight where the last blue light fades, down through the permanent darkness, through the cold and the pressure and the silence, to one of the most extraordinary environments on the surface of this planet. Tonight, we are exploring the deep sea. Before we begin, if you enjoy this kind of calm, unhurried journey through the wonders of the natural world, if this is the kind of content you like to fall asleep to or rest quietly alongside on a still evening, it would mean a great deal if you took a moment to like this video and subscribe to the channel. It helps more than you might expect, and it helps this channel continue making exactly this kind of content. And if you feel like leaving a comment, we would love to know where in the world you are listening from tonight and what time it is there. It is always interesting discovering where listeners are tuning in from around the world. Now, let us go down. The ocean covers approximately 71% of the surface of the Earth. It is the dominant feature of this planet, visible from space as a pale blue expanse that gives the Earth its name as the blue planet. And yet more than 80% of it remains unexplored and unmapped in detail. More of the ocean floor has never been directly observed than the surface of the Moon or the surface of Mars. The deep sea, the ocean below 200 meters, where sunlight can no longer fuel photosynthesis, is the largest living space on Earth by volume. It contains more than 95% of the total living space available to organisms on this planet, and most of it is unknown. Tonight we will visit 100 relaxing facts about this extraordinary world. We will move slowly and without hurry through the physical character of the deep, through the history of its exploration, through the creatures that inhabit it, through the geological wonders of its floor, through its connections to everyday life, and through the mysteries that still remain. There is no rush. The deep sea has been there for tens of millions of years. It will be there when we are done. Let us begin. Imagine the surface of the ocean on a calm day. The water is warm. Light penetrates it easily. You can see several meters down, perhaps more in clear tropical water. Fish move through shafts of sunlight. The water is blue and green and alive with color. This is the world most people mean when they think of the ocean. Now begin to descend. At 10 meters, the water is cooler. The red wavelengths of light are already gone, filtered out by the water above you, and the world has taken on a blue cast. At 50 meters, the light has dimmed considerably. At 100 meters, it is blue twilight. At 200 meters, you reach the boundary that oceanographers use to define the beginning of the deep sea, the point at which sunlight can no longer fuel photosynthesis. Below this line, no plant can grow using sunlight. The world changes character entirely. Between 200 and 1,000 meters lies the mesopelagic zone, sometimes called the twilight zone. Faint traces of blue light still penetrate here, enough to silhouette objects from below, but not enough to see by any ordinary standard. This is where the deep scattering layer lives, a dense concentration of organisms that rise toward the surface at night and descend again at dawn. It is where the great vertical migrations happen, and where many of the ocean's most remarkable small fish make their daily journeys. Below 1,000 meters, the last trace of sunlight disappears entirely. The bathypelagic zone, the midnight zone, extends from 1,000 to 4,000 meters, and it is in permanent, complete, absolute darkness. Not the darkness of a room with the curtains drawn, or of a cave with the lights off. Absolute darkness, the kind that has existed in these waters for millions of years without interruption, without a single photon of sunlight penetrating to disturb it. Fact number 1. The deep sea below 1,000 meters has been in permanent total darkness for longer than our species has existed. The temperature drops as you descend. In most of the deep ocean, the water settles at between 1 and 4 degrees Celsius, just above freezing, extraordinarily cold by the standards of the surface world. And this cold is consistent. The deep sea is one of the most thermally stable environments on Earth. Its temperature varying by fractions of a degree over years and decades, unlike the surface, which shifts with the seasons and the weather. Fact number 2. The deep sea is one of the most stable environments on Earth. Its temperature, salinity, and chemistry have remained nearly constant for tens of millions of years. The pressure increases relentlessly as depth increases by approximately 1 atmosphere for every 10 meters. At the surface, the pressure is 1 atmosphere, the weight of the air column above you. At 100 meters, it is 11 atmospheres. At 1,000 meters, it is 101 atmospheres. And at the bottom of the Mariana Trench, the deepest point in the ocean, reaching approximately 10,935 meters below sea level, the pressure is approximately 1,086 atmospheres. Fact number 3. The pressure at the bottom of the Mariana Trench is so extreme that water itself is compressed measurably. The water at that depth is approximately 5% denser than water at the surface. The Mariana Trench deserves a moment of attention. It is located in the western Pacific Ocean, east of the Mariana Islands. It is approximately 2,550 kilometers long and 69 kilometers wide, and it is so deep that if you were to take Mount Everest, the highest point on Earth's surface at approximately 8,849 meters, and place it at the bottom of the Challenger Deep, the deepest part of the trench, the summit would still be more than 2 kilometers below the surface of the ocean. Fact number 4. The Mariana Trench is estimated to be approximately 180 million years old, formed as the Pacific Plate slowly subducted beneath the Mariana Plate over geological time. The geography of the deep ocean floor is not the flat, featureless plain that many people imagine. Beneath the surface of the world's oceans lies a landscape of extraordinary variety. Mountains and valleys and plains and canyons that dwarf anything on the continents above. The mid-ocean ridge system, a continuous chain of underwater mountains running through every ocean basin, is the longest mountain range on Earth, stretching approximately 65,000 kilometers. It encircles the globe like the seam of a tennis ball, geologically active, punctuated with volcanoes and hydrothermal systems, constantly creating new seafloor at its crest through the process of seafloor spreading. Fact number 5. The mid-ocean ridge is the longest mountain range on Earth, longer than all the world's continental mountain ranges combined, and yet almost no one has ever seen it directly. Between the ridges and the trenches lie the abyssal plains, vast, flat expanses of seafloor covered in fine sediment. They cover approximately 40% of the ocean floor and are among the flattest large-scale surfaces on Earth, their topography smoothed by millions of years of sediment accumulation. In many areas, the abyssal plain extends for thousands of kilometers, with variations in elevation measured in only a few meters. Fact number 6. Abyssal plains are the flattest large-scale surfaces on Earth. Their extraordinary smoothness, the product of millions of years of slow, patient sediment accumulation. The deep sea, then, is not one environment, but a layered world of extraordinary variety. From the dim blue twilight of the Mesopelagic to the crushing blackness of the Hadal Zone, from the towering mountains of the mid-ocean ridge to the flat immensity of the abyssal plain. It is a world of extremes that has been quietly existing for longer than most of the life forms we know have been alive, and humans have only recently begun to visit it. That history of exploration, how we came to know the deep, and how much of it we still do not know, is where we are going next. For most of human history, the deep sea was not explored. It was imagined. And the imagination, it turned out, was not always accurate. In 1843, a British naturalist named Edward Forbes proposed what became known as the azoic hypothesis, the idea that below a certain depth, the ocean was completely lifeless. Forbes had conducted dredging surveys in the Aegean Sea and had noticed that organisms became progressively scarcer as depth increased. He extrapolated from his observations and concluded that below approximately 750 meters, no life could exist. The pressure was too great, the cold too severe, the darkness too complete. Fact number 7. The azoic hypothesis, the belief that the deep sea was completely lifeless, was one of the most significant scientific misconceptions of the 19th century, and it was held by many leading scientists for decades. The hypothesis was not disproved in Forbes's lifetime. He died in 1854 before the deep sea could be explored thoroughly enough to settle the question. But over the following decades, evidence accumulated that the deep sea was not lifeless. Creatures were being brought up in dredge nets from depths that Forbes had declared impossible for life to inhabit. The definitive disproof came from one of the most ambitious scientific expeditions in history. Fact number 8. The HMS Challenger expedition of 1872 to 1876 is considered the founding voyage of modern oceanography, the first systematic scientific exploration of the deep sea. The Challenger was a British Royal Navy corvette converted into a scientific research vessel and sent on a 4-year voyage around the world's oceans. Under the scientific leadership of Charles Wyville Thomson and John Murray, the expedition dredged and trawled at depths throughout the Atlantic, Pacific, Indian, and Southern Oceans. What they found demolished the azoic hypothesis entirely. Fact number 9. The HMS Challenger expedition collected 4,717 new species of marine organisms, demonstrating beyond doubt that life existed throughout the deep ocean at every depth the expedition sampled. The Challenger traveled approximately 68,890 nautical miles during its 4-year voyage, an extraordinary undertaking for the steam and sail technology of the era. Its scientific results, published over the following 2 decades in 50 volumes, formed the foundation of modern oceanography. But knowing that the deep sea contained life was different from being able to observe it directly. For that, a new technology was needed. In 1930, an engineer named Otis Barton and a naturalist named William Beebe developed the bathysphere, a steel sphere approximately 1.5 meters in diameter, with small quartz portholes and a single entry hatch. It was lowered on a cable from a surface ship. It could not maneuver independently, could not surface under its own power, and if the cable broke, the occupants would be lost. Despite these limitations, it allowed human beings to descend far deeper than they had ever gone before. Fact number 10. In 1932, William Beebe and Otis Barton descended to 923 meters in the bathysphere, a world depth record at the time. And Beebe broadcast descriptions of what he saw through a telephone cable to the surface. What Beebe saw through those small quartz portholes changed his understanding of the ocean. Bioluminescent organisms drifted past in the darkness, creatures of forms he had never seen, some entirely new to science. He described the experience as looking out at a world that no human eye had ever seen before. The next great milestone came nearly 3 decades later, on January 23, 1960. Fact number 11. On that date, Don Walsh of the United States Navy and Jacques Piccard, son of the bathyscaphe's designer Auguste Piccard, descended to the bottom of the Challenger Deep in the Trieste, reaching a depth of approximately 10,900 meters and becoming the first human beings to visit the deepest point in the ocean. They spent approximately 20 minutes on the bottom, observing, to their considerable surprise, a flatfish resting on the sediment and shrimp moving through the water. Life at the very deepest point of the ocean. The azoic hypothesis was definitively and spectacularly wrong. The next revolution in deep-sea exploration came not from reaching new depths, but from discovering what existed at familiar ones. Fact number 12. In 1977, scientists aboard the research submersible Alvin descended to the seafloor near the Galapagos Rift in the Pacific and discovered hydrothermal vents, cracks in the seafloor emitting superheated mineral-rich water, surrounded by extraordinary communities of organisms unlike anything previously known to science. The discovery of hydrothermal vents completely changed scientific understanding of where life can exist and how it can be sustained, not from sunlight, but from the chemical energy of the Earth's interior. We will return to these extraordinary places in detail in a later section. Exploration continued. In 1984, cold seeps, areas where hydrocarbon-rich fluids seep from the seafloor at ambient temperature, were discovered in the Gulf of Mexico, revealing yet another chemosynthetic ecosystem on the ocean floor. In 1985, Robert Ballard used remotely operated vehicles to locate the wreck of the RMS Titanic at a depth of approximately 3,800 meters in the North Atlantic. Fact number 13. Robert Ballard's discovery of the Titanic in 1985 demonstrated the practical power of remotely operated vehicles for deep-sea exploration. vehicles that could go where human beings could not, stay as long as needed, and return with photographs and samples. In 2012, filmmaker James Cameron descended solo to the Challenger Deep in his submersible, the Deep Sea Challenger, spending approximately 3 hours on the bottom collecting samples and conducting scientific observations. Between 2018 and 2019, the Five Deeps expedition completed the first crewed dives to the deepest point in each of the 5 oceans. Fact number 14. Approximately 2,000 new deep-sea species are discovered per year, a rate that suggests the deep ocean will continue yielding biological surprises for generations to come. The deep sea is a frontier whose exploration has barely begun. More than 80% of the ocean remains unmapped in detail. The majority of its organisms remain undescribed. The history of deep-sea exploration is not a completed chapter. It is a story still being written, with most of its pages still blank. And what those blank pages contain, the organisms, the ecosystems, the geological features still to be discovered, will be the subject of scientific journeys for centuries to come. But first, we should understand how the deep sea is fed, how life sustains itself in a place where no sunlight reaches, where the only food is what drifts down from the world above. That question, and its elegant, slow, continuous answer, is where we are going next. In the permanent darkness of the deep sea, it snows. Not water snow, not ice, but a slow, continuous, gentle rain of organic material, dead organisms, shed cells, fecal pellets, fragments of mucus and shell and plant matter that drifts downward from the sunlit surface of the ocean, falling through hundreds and thousands of meters of dark water before settling on the seafloor below. This is marine snow, and it is the foundation of life in the deep sea. Fact number 15. Marine snow, the slow rain of organic material falling from the surface ocean to the deep sea floor, is the primary food source for the vast majority of deep sea organisms. Marine snow particles range from microscopic fragments to aggregates several centimeters across. They form when organic material in the surface ocean, dead phytoplankton, zooplankton carcasses, fecal pellets, shed mucus from filter-feeding organisms, clumps together under the influence of surface tension and biological stickiness into particles large enough to sink. Under a light source in the dark water, they appear exactly as their name suggests, a slow, drifting snowfall in 3 dimensions, falling not downward in a straight line, but drifting and tumbling as currents move them, taking irregular paths towards the distant floor. Fact number 16. The descent of marine snow from the surface ocean to the abyssal plain can take weeks to months. A particle that leaves the surface today may not reach the seafloor 4,000 meters below until months from now. Imagine following a single particle of marine snow on its journey. It begins as part of a phytoplankton bloom in the sunlit surface ocean, perhaps a diatom, or a fragment of a zooplankton fecal pellet, or a shed scale from a small fish. It sinks slowly, drifting with the currents, occasionally being consumed by organisms in the mesopelagic zone and incorporated into new fecal pellets that then continue sinking. It passes through the twilight zone, still drifting, still descending. It enters the midnight zone, the permanent darkness of the bathypelagic, and continues downward. Weeks pass, months, and eventually, after a journey of extraordinary slowness through thousands of meters of dark water, it settles on the abyssal plain. Here, it joins the layer of sediment that has been accumulating on the seafloor for millions of years. Fact number 17. Deep-sea sediment accumulates at a rate of approximately 1 to 10 centimeters per 1,000 years, meaning the sediment layer on the abyssal plain is extraordinarily thin relative to the time it represents, but extraordinarily rich in the biological information it contains. The process by which marine snow transfers carbon from the productive surface ocean to the deep sea is called the biological pump. At the surface, phytoplankton absorb carbon dioxide from the atmosphere and convert it into organic carbon through photosynthesis. When these organisms die or are consumed, some fraction of the carbon they contain sinks as marine snow rather than being recycled at the surface. This carbon is effectively removed from the atmosphere and stored in the deep ocean, contributing to the ocean's role as a vast carbon sink. Fact number 18. The ocean stores approximately 50 times more carbon dioxide than the atmosphere, much of this carbon reaching the deep ocean through the biological pump carried by marine snow. But the deep sea is not fed only by the passive sinking of marine snow. Each night, the deep sea comes to the surface. The diel vertical migration is the largest daily animal migration on Earth, and most people have never heard of it. Every evening, as the sun sets, billions of organisms, primarily copepods, krill, lanternfish, bristlemouths, and other small mesopelagic animals, migrate upward from their daytime depths of several hundred meters toward the surface ocean, where they feed on the abundant phytoplankton and zooplankton of the productive surface layer. And every dawn, as the light returns, they descend again to the safety of depth. Fact number 19. The diel vertical migration involves billions of organisms and represents the largest coordinated movement of animals on Earth, occurring every single night across every ocean in the world. This migration does more than move organisms. It actively pumps carbon from the surface to the deep. The migrants eat at the surface and respire at depth, releasing carbon dioxide into deep water rather than at the surface. This active transport accelerates the biological pump, transferring carbon to depths where it will remain out of the atmosphere for centuries or longer. Fact number 20. The diel vertical migration pumps an estimated 1 to 2 gigatons of carbon from the surface to the deep ocean each year, making it one of the most significant carbon transport processes on Earth. The deep sea floor, where marine snow ultimately accumulates, is a world of extraordinary biological richness per gram of sediment. Fact number 21. A single teaspoon of deep-sea sediment may contain millions of bacterial cells representing thousands of distinct species, a microbial city compressed into a pinch of mud. The marine snow that feeds these bacteria has been falling continuously. Right now, as you listen, drifting downward through the darkness of the deep ocean in the same slow, patient way it has been falling for hundreds of millions of years, long before the first fish existed, long before the first animals existed. The rain of organic material from the sunlit surface to the dark floor is one of the most ancient and continuous processes in the ocean. a slow, quiet transfer of life's energy from the world of light to the world of permanent darkness. Researchers believe that the deep sea's dependence on marine snow from the surface means that changes in surface ocean productivity, in the abundance of phytoplankton and the organisms that feed on them, directly affect the amount of food available to deep sea communities. The surface and the deep are connected by this slow rain, and what happens in one affects the other, separated as they are by thousands of meters and weeks of falling time. The deep sea, then, is sustained from above, fed by a snow that never stops. But the deep sea is not only dark. Within that darkness, something remarkable is happening. Something that challenges the very idea that the deep is a world without light. That is where we are going next. But the deep sea is not lightless. In the permanent darkness of the bathypelagic zone, light is produced constantly, not by the sun, not by any external source, but by the organisms themselves. Living light, biological light, light produced through chemical reactions in the tissues of animals and bacteria and single-celled organisms distributed throughout the deep ocean. Fact number 22. Approximately 76% of deep-sea organisms are estimated to produce bioluminescence, making living light not a novelty in the deep sea, but a near-universal feature of its inhabitants. Bioluminescence is produced when a light-emitting compound called luciferin is oxidized in the presence of an enzyme called luciferase. The reaction produces light with almost no heat, a cold light, efficient and precisely controlled. Different organisms produce different colors, most commonly blue and green, which travel furthest through seawater. But some produce red, yellow, or white light for specific purposes. Imagine descending through the midnight zone in a submersible with all external lights switched off. In the absolute blackness of that environment, you would not see nothing. You would see a world of flickering, pulsing, drifting light, blue and green flashes from organisms disturbed by your passage, the steady glow of bioluminescent bacteria, the slow pulse of siphonophores extending through the water like living strings of lights, the brief, bright flash of a fish startled by your presence. The deep sea at night, which is to say, always, is a world of light. Fact number 23. The deep sea has its own light, produced not by the sun, but by the organisms themselves. A world of bioluminescent displays that have been occurring continuously in the permanent darkness for hundreds of millions of years, witnessed almost entirely by no one. Bioluminescence serves many purposes in the deep sea. The variety of its uses tells us something important about the sophistication of deep sea life. This is not simply a random chemical reaction, but a precisely evolved communication and hunting system. One of the most elegant uses is counter-illumination. Many mesopelagic fish have rows of light-producing organs called photophores along their undersides. These photophores produce a soft, downward-directed glow that precisely matches the faint residual sunlight filtering down from above. From below, a fish using counter-illumination has no silhouette. Its bioluminescent underside blends seamlessly with the background light, making it effectively invisible to predators looking upward. Fact number 24. Counter-illumination is a bioluminescent camouflage technique used by mesopelagic fish. The photophores on their undersides produce light, matching the dim, downwelling sunlight from above, eliminating the fish's silhouette from the perspective of predators below. The anglerfish uses bioluminescence for a different purpose entirely. The female anglerfish, for it is the female that has the lure, carries on her forehead a modified dorsal spine tipped with a small bulb called the esker. The esker contains bioluminescent bacteria that produce a steady glow in the darkness. The anglerfish dangles this lure near its enormous mouth and waits. Prey, attracted by the light, approach, and the anglerfish strikes. Fact number 25. The bioluminescent lure of the anglerfish is not produced by the fish itself. The light comes from bacteria living within the esker. The anglerfish and its bacterial light source have a relationship not unlike that of the coral and its zooxanthellae. Some deep-sea fish have taken bioluminescence a step further. The dragonfish, a slender predator of the mesopelagic zone, produces not blue or green light, but red. Most deep-sea organisms have eyes adapted only to blue and green wavelengths, the colors that travel furthest in seawater. They cannot see red light at all. This means the dragonfish carries what is effectively an invisible lantern, a red bioluminescent light that illuminates its prey without alerting other organisms to its presence. Fact number 26. The dragonfish produces red bioluminescent light that is invisible to most other deep-sea organisms, giving it a private illumination system that functions as a secret lantern in a world where most other animals are effectively blind to that color. Among the most extraordinary bioluminescent organisms in the deep sea are the siphonophores. Siphonophores are colonial organisms, not a single animal, but a colony of many individual organisms called zooids, each specialized for a different function. Some for swimming, some for feeding, some for reproduction. Together, they function as a single coordinated entity, and together they can produce bioluminescent light along their entire length. Fact number 27. The siphonophore, Praia dubia, can reach lengths of 40 to 50 meters, making it one of the longest animals ever recorded on Earth, and produces bioluminescent light along its entire colonial body. The deep scattering layer, that dense concentration of mesopelagic organisms that reflects sonar signals, was initially mistaken for the ocean floor when it was first detected during World War II. Sonar operators noticed a layer that appeared to be the seafloor, but that moved, rising toward the surface at night and descending during the day. It was only later understood to be the bioluminescent community of organisms undertaking the diel vertical migration. Fact number 28. The deep scattering layer was initially mistaken for a false ocean floor by sonar operators during World War II. The dense bioluminescent organisms reflecting sonar signals just as the sea floor would. The deep sea, then, is not a world of darkness, but a world of a different kind of light. A world where light is biological, intimate, purposeful, and everywhere. Every flash, every glow, every pulse of bioluminescence in the midnight zone is a communication, a lure, a defense, or a disguise, evolved over millions of years in a world where darkness makes light extraordinarily precious. And in this world of living light live some of the most extraordinary creatures that evolution has ever produced. Those creatures are where we are going next. The deep sea has been producing extraordinary organisms for hundreds of millions of years, shaped by conditions, extreme pressure, permanent darkness, cold temperatures, scarce and unpredictable food that have no close parallel in any other environment on Earth. The result is a menagerie of creatures unlike anything in the sunlit surface world. Let us visit some of them. We begin with the largest eyes in the animal kingdom. The giant squid, Architeuthis dux, is one of the most famous of all deep-sea animals, partly because it was known from sailors' accounts and strangled remains for centuries before anyone photographed a living specimen. It can reach lengths of up to 13 meters. Its eyes can reach 30 centimeters in diameter, roughly the size of a dinner plate, the largest eyes of any living animal. Fact number 29. The giant squid's enormous eyes evolved to detect the faint bioluminescent flashes produced by its primary predator, the sperm whale. The eyes are large enough to capture the dim blue bioluminescent light at depths where no other light exists. The colossal squid, Mesonicoteuthis hamiltoni, is heavier than the giant squid, if not always as long, and has eyes estimated at up to 27 centimeters in diameter with built-in photophores, light-detecting structures that may help it sense bioluminescent activity in its environment. It is one of the least studied large animals on Earth. Very few complete specimens have ever been examined. Fact number 30. The colossal squid has hooks on its tentacles as well as suckers, rotating hooks that can swivel freely, making it among the most formidable predators in the deep southern ocean. The barrel-eye fish, Macropinna microstoma, is a creature of quiet wonder. Its most striking feature is immediately visible. The top of its head is covered by a transparent, fluid-filled dome, and within that dome sit two large green tubular eyes that can rotate upward to look for prey silhouetted against the faint light from above. For many years, the transparent dome was not recognized as such. The fish's head appeared different in specimens brought to the surface where the dome collapsed. It was only through observation of living specimens by remotely operated vehicles that the full extraordinary nature of the barrel-eye's visual system was understood. Fact number 31. The barrel-eye fish's tubular eyes can rotate. They can look upward through the transparent dome to detect prey silhouetted against dim surface light, then rotate forward to look ahead when the fish is actively pursuing food. The fangtooth fish, Anoplogaster cornuta, is a small fish of the mesopelagic and bathypelagic zones that has the largest teeth relative to body size of any fish in the ocean. Its teeth are so large that the fish cannot fully close its mouth. The long fangs of the lower jaw fit into corresponding sockets in the roof of the mouth when the fish bites, allowing the jaw to close at all. Fact number 32. The fangtooth fish's teeth are so large relative to its body that special sockets in the roof of its mouth accommodate the lower fangs, preventing the teeth from piercing the fish's own brain when its mouth closes. The Dumbo octopus, named for the large ear-like fins that extend from the sides of its mantle, is the deepest living known octopus, having been observed at depths of up to 7,000 meters. It moves through the water by flapping these fins and using its arms to steer, and it feeds on small crustaceans and worms on the sea floor. Fact number 33. The Dumbo octopus can flush color through its skin and change shape by retracting or extending its arms. It is a shapeshifter of the deep, capable of taking dramatically different forms within seconds. The vampire squid, Vampirotudis infernalis, which translates to vampire squid from hell, is neither a squid nor an octopus. It belongs to its own order, Vampiromorphida, and occupies a unique ecological niche in the deep sea. Rather than hunting prey, the vampire squid feeds on marine snow, drifting through the water and collecting organic particles using long, sticky filaments. Fact number 34. The vampire squid is the only known cephalopod that does not hunt living prey. It feeds entirely on marine snow and detritus, making it a gentle filter feeder in a phylum otherwise dominated by active predators. Deep-sea gigantism, the tendency of deep-sea organisms to grow much larger than their shallow water relatives, has produced some remarkable creatures. Giant isopods, relatives of the common pillbug found in gardens, can reach 50 centimeters in length, compared to their surface relatives, which are typically a few centimeters. Giant amphipods, giant sea spiders with leg spans up to 70 centimeters, and giant ostracods all illustrate this tendency toward larger body size in the cold, slow metabolizing deep sea. Fact number 35. Deep-sea gigantism is thought to result from a combination of cold temperatures, slowing metabolism and extending lifespan, abundant food from marine snow, and reduced predation pressure compared to shallow water environments. Xenophyophores deserve their own moment. These are single-celled organisms, a single cell, one cell, not a colony, that can reach 20 centimeters in diameter, making them among the largest individual cells known to science. They accumulate sediment particles and build elaborate structures around their single-cell body, creating architectural forms of considerable complexity for a single-celled organism. Fact number 36. A xenophyophore is one organism, one cell, that can grow to the size of your fist, making it among the largest single-celled organisms on Earth. The Greenland shark moves through Arctic and deep Atlantic waters with a patience that is almost geological. It grows approximately 1 centimeter per year. It may not reach sexual maturity until it is approximately 150 years old, and it can live for more than 400 years, possibly the longest-lived vertebrate animal on Earth. Fact number 37. A Greenland shark alive today may have been born during the 17th century, swimming slowly through cold, dark water for longer than any country currently existing has been an independent nation. In 2023, a snailfish, Pseudoliparis belyaevi, was filmed at a depth of 8,336 meters in the Japan Trench, setting a new record for the deepest fish ever observed. And in Monterey Canyon, a female deep-sea octopus, Granolidon boreopacifica, was observed brooding her clutch of eggs for 53 months. She never left. She never ate. For 4.5 years, she tended her eggs in the cold darkness of a seamount. And when the eggs finally hatched, she died. Fact number 38. The deep-sea octopus's 53-month egg brooding is the longest known brooding period of any animal, an act of extraordinary patience in a world already defined by patience. The deep sea is, in many ways, a world of patience, of slowness, of long lives lived at a pace that makes human timescales feel hurried. And nowhere is this patience more dramatically expressed than in the communities that live not by marine snow, but by the chemical energy of the earth itself. Those communities are where we are going next. On the 18th of February, 1977, the research submersible Alvin descended to the seafloor near the Galapagos Rift in the eastern Pacific Ocean. The scientists aboard were geologists. They were looking for evidence of hydrothermal activity, cracks in the seafloor where seawater percolating into the crust was being heated by the magma below and expelled back into the ocean. They were expecting to find warm water and perhaps some chemical anomalies. What they found changed biology. As Alvin approached the seafloor in the expected area, the water temperature sensors began to register an anomaly. The water was warmer than expected. And then, in the lights of the submersible, the seafloor came into view, and it was covered in life. Dense, extraordinary, completely unexpected life. Clusters of giant white clams, mats of white bacteria, and rising from the seafloor, clusters of animals that none of the scientists had ever seen before. Long white tubes, topped with vivid red plumes, waving gently in the warm water, rising from cracks in the seafloor. Fact number 39. The discovery of hydrothermal vent communities in 1977 was completely unexpected. The geologists aboard Alvin had no biologist with them and had to call a biologist on the surface ship by telephone to help identify what they were seeing. What the scientists had found was a community of organisms sustained not by sunlight, but by the chemical energy of the earth itself. Hydrothermal vents form where seawater percolates down through cracks in the sea floor near mid-ocean ridges, is heated by the magma below to temperatures that can reach 400 degrees Celsius, and then rises back through the crust laden with dissolved minerals, particularly hydrogen sulfide. As this superheated mineral-rich water is expelled into the cold surrounding ocean, the minerals precipitate out, forming the characteristic black or white chimneys that give different vent types their names: black smokers and white smokers. Fact number 40. The water emerging from black smoker hydrothermal vents can reach 400 degrees Celsius, far above the normal boiling point of water, but remains liquid because the extreme pressure of the deep sea raises the boiling point dramatically. The hydrogen sulfide in hydrothermal vent water is the key to everything. Bacteria and archaea living in and around the vents can oxidize hydrogen sulfide, using the energy released by this chemical reaction to produce organic compounds, just as photosynthetic organisms use the energy of sunlight. This process, chemosynthesis, is the foundation of the entire vent food web. Fact number 41. Chemosynthesis, the production of organic matter from chemical reactions rather than from sunlight, was first understood through the study of hydrothermal vent communities and represents an entirely independent foundation for life, separate from photosynthesis. The organisms that inhabit hydrothermal vents have evolved remarkable adaptations to exploit this chemical energy. Among the most striking are the tube worms, Riftia pachyptila, which can reach 3 meters in length and extend vivid red plumes into the vent water to absorb hydrogen sulfide and oxygen. These plumes are rich in hemoglobin, the same protein that makes blood red, which binds both hydrogen sulfide and oxygen and transports them to bacteria living within a specialized organ called the trophosome. Fact number 42. Riftia pachyptilla tube worms have no mouth, no stomach, and no digestive system of any kind. They are entirely sustained by the chemosynthetic bacteria living within their tissues, which process the chemicals delivered by the tube worm's circulatory system. Fact number 43. Riftia pachyptilla can grow up to 85 centimeters per year under favorable conditions, one of the fastest growth rates of any marine invertebrate. The yeti crab, Kiwa hirsuta, discovered near hydrothermal vents in the Pacific, has long silky hairs on its claws that harbor colonies of chemosynthetic bacteria. The crab waves its hairy claws near the vent emissions, exposing the bacteria to the hydrogen sulfide and warm water that fuel their growth, and then grazes on the bacteria it has cultivated. The yeti crab is, in the most literal sense, a farmer. Fact number 44. The yeti crab waves its bacteria-covered claws in the warm vent water to cultivate chemosynthetic bacteria and then grazes on these bacteria, making it one of the clearest examples of animal agriculture in the non-human world. In the Atlantic Ocean, a different kind of hydrothermal vent system produces a very different landscape. The Lost City hydrothermal vent field, discovered in 2000 on the Mid-Atlantic Ridge, features chimneys not of dark mineral sulfides, but of pale white carbonate, calcium carbonate, and magnesium hydroxide precipitated from the alkaline vent fluids. These white towers can reach 60 meters in height, taller than a 10-story building, and they rise from the seafloor in clusters that resemble the ruins of an ancient architecture. Fact number 45. The Lost City vent field features white carbonate towers up to 60 meters tall, among the most visually striking structures on the ocean floor, built not by any biological process, but by the precipitation of minerals from alkaline vent fluids. The chemistry of the Lost City vents is fundamentally different from black smoke vents. The fluids are alkaline rather than acidic, and they support a distinctive microbial community dominated by archaea. Researchers believe the chemistry of systems like Lost City may resemble the conditions under which life on Earth first arose. Fact number 46. The alkaline hydrothermal vent theory of the origin of life proposes that the first living things may have emerged in systems similar to the Lost City, where the alkaline chemistry and porous mineral structures of the vents could have provided the conditions for the first biochemical reactions. Hydrothermal vent communities are ephemeral. A single vent may be active for decades before the geological processes supporting it cease and the flow of superheated water stops. When a vent shuts down, the organisms that depend on it must disperse to new vents or die. This creates a dynamic of colonization and extinction across the deep sea floor. Communities appearing where new vents open, disappearing when old ones close. Fact number 47. The organisms of hydrothermal vents must colonize new vent sites as old ones shut down, driving a process of dispersal and recolonization across the deep sea floor that has been occurring for as long as mid-ocean ridges have been geologically active. The discovery of life at hydrothermal vents fundamentally changed one of the most basic assumptions of biology. the assumption that all life ultimately depends on sunlight. It demonstrated that life can exist, can flourish, can build extraordinary communities of diverse organisms in complete and permanent darkness, sustained entirely by the chemical energy of the planet's interior. And the vents are not the only place where this alternative foundation for life expresses itself on the deep sea floor. The other worlds of deep sea chemosynthetic life, the cold seeps and whale falls and underwater lakes, are where we are going next. The hydrothermal vent is the most famous of the deep sea's chemosynthetic ecosystems, but it is not the only one. Across the ocean floor, in patterns that are still being mapped and understood, there are other places where chemical energy, rather than sunlight, sustains communities of extraordinary organisms, each one a world within the world of the deep sea, each one with its own distinctive character. The first of these other worlds was discovered in 1984. In that year, researchers using a submersible in the Gulf of Mexico descended to an area of seafloor that had been identified as geologically unusual, an area where the sediment appeared disturbed and where chemical measurements suggested something unusual was entering the water from below. What they found was a cold seep. Fact number 48. Cold seeps are areas of the seafloor where hydrocarbon-rich fluids, primarily methane and hydrogen sulfide, seep upward through the sediment from geological deposits below at ambient temperature rather than the superheated temperatures of hydrothermal vents. Cold seeps do not produce spectacular chimneys or billowing clouds of superheated water. They are quieter than hydrothermal vents, the fluids emerging slowly, the hydrogen sulfide and methane diffusing upward through the sediment and into the water column above. But the chemistry they release, like the chemistry of hydrothermal vents, provides energy for chemosynthetic bacteria and archaea that form the base of a food web. Around cold seeps, dense communities of mussels, clams, tube worms, and other organisms cluster, sustained by the chemical energy of the seeping fluids. White bacterial mats cover the sediment. The smell of hydrogen sulfide, detectable by chemical sensors on submersibles, pervades the immediate area. It is a world that feels, in some ways, like the twilight of an older Earth. Above the seafloor, another kind of temporary deep-sea ecosystem is periodically created, not by geological processes, but by death. When a large whale dies in the ocean, its body sinks, slowly at first, as decomposition begins, then faster as the gases of decay are dissolved or released and the carcass loses buoyancy. Eventually, after a journey that may take weeks, the whale's body reaches the seafloor, and there, something remarkable begins to happen. Fact number 49. A whale fall. The body of a dead whale, resting on the deep sea floor, can sustain a diverse community of organisms for 50 to 100 years, passing through distinct ecological stages as the carcass is progressively consumed. The first stage, the mobile scavenger stage, begins immediately. Hagfish, sleeper sharks, and other large scavengers detect the chemical plume of the carcass from kilometers away and arrive to consume the soft tissue. Within months to years, depending on the size of the whale, the soft tissue is gone and the skeleton remains. The second stage, the enrichment opportunist stage, sees smaller organisms colonizing the bones, and the enriched sediment around the skeleton. Polychaeta worms, crustaceans, and other invertebrates arrive in enormous numbers, drawn by the unusual abundance of organic material. The third and longest stage, the sulfophilic stage, is the most remarkable. The fats and oils within the whale's bones begin to be broken down by anaerobic bacteria, releasing hydrogen sulfide into the surrounding sediment. And chemosynthetic bacteria colonize the bones, exploiting this hydrogen sulfide in exactly the same way as bacteria at cold seeps and hydrothermal vents. Fact number 50. During the sulfophilic stage of whale fall decomposition, the whale's skeleton becomes a chemosynthetic island on the seafloor, supporting a community of organisms sustained by the same chemical energy as hydrothermal vent communities, but using the whale's own body chemistry as the fuel. Among the most remarkable inhabitants of whale falls are the oceanography worms, sometimes called zombie worms. These small polychaeta worms bore into whale bones using root-like structures that penetrate the bone matrix. Within these roots, symbiotic bacteria digest the fats and proteins of the bone, and the worm absorbs the products. Oceanography worms have no mouth and no digestive system. Like the tube worms of hydrothermal vents, they have outsourced their digestion to symbiotic bacteria. Fact number 51. Zombie worms, oceanography species, were first described in 2004 from whale falls in Monterey Bay. The visible worm is female. Microscopic males live within the female's body, existing solely to fertilize her eggs. Elsewhere on the deep sea floor, in locations where thick salt deposits were left by ancient evaporated seas, there exists one of the most visually striking features of the deep ocean: underwater brine lakes. Where salt deposits on the seafloor dissolve, the dense brine that results accumulates in depressions in the seafloor. This brine, far saltier and therefore far denser than the surrounding seawater, does not mix with the overlying water. It forms a distinct liquid layer with its own visible surface and visible shores. From a submersible, it looks exactly like what it is: a lake within an ocean. Fact number 52. Underwater brine lakes on the ocean floor have a distinct surface that appears as a shimmering boundary between the normal seawater above and the dense brine below. Animals that accidentally swim into a brine lake are quickly overwhelmed by the extreme salinity and sink to the bottom, sometimes preserved by the anoxic conditions. The brine lakes have their own extremophile communities, bacteria and archaea adapted to the extreme salinity of the brine, living in an environment that would be instantly lethal to most other organisms. Deep-sea coral gardens complete this picture of diversity. In cold, dark water throughout the world's deep oceans, corals grow without the zooxanthellae that shallow water corals depend on. They filter organic particles from passing currents, growing with extraordinary slowness in water near the freezing point. Fact number 53. Some deep-sea coral colonies have been dated to more than 4,000 years old using radiocarbon dating, alive and growing since before the construction of the Egyptian pyramids, tended only by the slow currents of the deep sea. The deep sea floor, then, is not a uniform desert. It is a landscape of distinct ecosystems, hydrothermal vents and cold seeps and whale falls and brine lakes and coral gardens, each one a world in itself, each one sustained by different energy sources and inhabited by different communities of organisms scattered across a floor that is largely unmapped and mostly unvisited. And in some parts of that floor, the pressure is so extreme, the depth so great, that even these communities give way to something else entirely. That deepest of all environments, the Hadal Zone, is where we are going next. Below 6,000 meters, the ocean changes character. Most of the deep sea, the abyssal zone, lies between 4,000 and 6,000 meters. It is cold, dark, and pressurized, but it is also the most extensive habitat in the ocean, covering vast areas of the sea floor across every ocean basin. The abyssal zone has been visited by submersibles and sampled by dredges enough that we have at least some picture of its inhabitants. Below 6,000 meters, you enter the Hadal Zone. The Hadal Zone takes its name from Hades, the Greek underworld, a name chosen to reflect not the character of the zone itself, but the sense of its remoteness and depth, its position at the furthest extreme of the accessible world. The Hadal Zone encompasses the deepest portions of the world's ocean trenches, narrow, elongated depressions in the sea floor where tectonic plates subduct beneath one another, creating some of the most extreme environments on Earth. Fact number 54. There are approximately 37 Hadal trenches in the world's oceans, one in each major subduction zone. And together, they cover less than 1% of the ocean floor, but represent the most extreme pressure environments accessible to life. The pressure in the Hadal Zone is crushing by any ordinary standard. At 8,000 meters, the pressure is approximately 800 atmospheres. At the bottom of the Challenger Deep, it reaches approximately 1,086 atmospheres. These pressures would instantly destroy the cells of most surface organisms, disrupting membranes, compressing proteins into non-functional shapes, collapsing gas-filled structures like swim bladders. Yet, the Hadal Zone is inhabited. The dominant organisms of the Hadal Zone are small crustaceans called amphipods, relatives of the sandhoppers found on beaches worldwide. Hadal amphipods have adapted to the extreme pressure of the trenches and are often found in remarkable densities, drawn in large numbers to baited traps lowered by researchers. Fact number 55. Hadal amphipods can reach densities of thousands of individuals in a single baited trap lowered into a deep trench, their abundance reflecting an adaptation to exploiting the rare but concentrated food sources that reach Hadal depths. How do Hadal organisms survive pressures that would destroy surface organisms? One key adaptation involves a molecule called trimethylamine oxide, TMAO, found in high concentrations in the tissues of deep-sea fish and other Hadal organisms. TMAO is a pressure-stabilizing molecule that counteracts the effects of pressure on proteins and membranes, allowing biological molecules to function at depths where they would otherwise be compressed into non-functional shapes. Fact number 56. The concentration of trimethylamine oxide in deep-sea fish increases with depth. The deeper the fish lives, the more TMAO its tissues contain, suggesting that TMAO concentration is a key adaptation to high-pressure environments. The fish that dominate the Hadal Zone are not the large predators of shallow water, but the snailfish, small, gelatinous, pale-colored fish of the family Liparidae. Their gelatinous bodies and the absence of a gas-filled swim bladder make them well suited to extreme pressure. There are no gas-filled spaces to be compressed. In 2023, a snailfish, Pseudoliparis belyaevi, was filmed at 8,336 meters in the Japan Trench. Fact number 57. The snailfish observed at 8,336 meters in the Japan Trench in 2023 is the deepest fish ever recorded, living at a pressure that exceeds 800 atmospheres. The Hadal Zone is also, perhaps surprisingly, one of the most microplastic-contaminated environments on Earth. Researchers collecting water samples and sediment from deep trenches have found microplastics, tiny fragments of synthetic polymers, present at every depth sampled, including the very deepest points. Plastic bags have been found in the stomachs of Hadal creatures at depths exceeding 10,000 meters. Microplastic fibers have been found in the tissues of amphipods from the Mariana Trench. Fact number 58. The Mariana Trench, the deepest place on Earth, more than 10,000 meters below the surface, contains microplastics in its water column, sediment, and in the tissues of its organisms, demonstrating that human-produced materials have reached the most remote location on the planet. Fact number 59. A plastic bag, the most ordinary of human-made objects, has been found at the bottom of the Mariana Trench, in a place that no human had visited until 1960, and that fewer than a dozen people have ever seen directly. There is something worth sitting with in that image. The Hadal Zone, the most remote and extreme environment on Earth's surface, a place requiring the most sophisticated technology to visit, a place so extreme that reaching it represents one of the great engineering challenges of the modern era, contains the detritus of ordinary human life, the materials of everyday convenience, manufactured and discarded at the surface, have found their way to the deepest places on the planet through the slow drift of ocean currents and the sinking of particles through the water column. The Hadal Zone is simultaneously the most remote environment on Earth and one of the most demonstrably connected to human activity. Yet, the organisms that live there, the amphipods, the snailfish, the polychaete worms and sea cucumbers, and single-celled organisms of the deepest trenches, continue to live their extraordinarily adapted lives in the cold and the dark and the pressure, as they have for millions of years. Fact number 60. Despite being one of the least studied environments on Earth, the Hadal Zone is known to harbor hundreds of distinct species adapted specifically to its extreme conditions, organisms found nowhere else on the planet. Below the organisms of the Hadal Zone, below the water column entirely, lies the seafloor itself. And the seafloor of the deep ocean is not simply a passive substrate for the organisms above it. It is a record, patient, detailed, extraordinarily long, of the history of the Earth itself. That record is where we are going next. The deep sea floor is a library. Not a library of books, of course, but a library of a different kind. A physical archive of the Earth's past, written in the chemistry of microscopic shells and the layers of fine sediment that have been accumulating on the abyssal plain for millions of years. If you know how to read it, the seafloor contains one of the most detailed records of Earth's climate, its chemistry, its biological productivity, and its geological history that exists anywhere on the planet. The reading is done one core at a time. When a research vessel deploys a sediment corer, a long metal tube driven into the sea floor by gravity or by a piston mechanism, it extracts a cylinder of sediment that may be several meters long. Each centimeter of that cylinder represents approximately 1,000 years of accumulation. The bottom of a 5-meter core may contain sediment that was deposited 5 million years ago. And within that sediment, preserved with extraordinary fidelity, are the remains of the organisms that lived in the surface ocean above during all those millions of years. Fact number 61. Deep-sea sediment accumulates at approximately 1 to 10 centimeters per 1,000 years, meaning a sediment core 5 meters long may contain a continuous record of ocean conditions extending 5 million years into the past. The primary contributors to deep-sea sediment are the shells of foraminifera, microscopic organisms related to amoebas that secrete elaborate calcium carbonate shells and live in the surface and near-surface ocean. When foraminifera die, their shells sink slowly to the sea floor, accumulating in layers. In some areas of the deep ocean, foraminifera shells make up the majority of the sediment, thick deposits of what is called foraminiferal ooze, covering vast areas of the abyssal plain. Fact number 62. Foraminifera shells preserve a chemical record of the ocean conditions in which they grew. The ratio of oxygen 18 to oxygen 16 isotopes in their calcium carbonate reflects the temperature of the water and the volume of ice locked in glaciers at the time they formed. By analyzing the oxygen isotope ratios in foraminifera shells at different depths in a sediment core, scientists can reconstruct past ocean temperatures decade by decade, century by century, across millions of years. This technique, developed by Cesare Emiliani in the 1950s, transformed paleoclimatology. For the first time, it was possible to read the temperature of the ocean in the distant past from the chemistry of microscopic shells preserved in deep-sea mud. Fact number 63. Deep-sea sediment cores combined with ice cores from Antarctica and Greenland provide the most detailed records of Earth's climate history available to science, extending the temperature record millions of years before any human observation and revealing the patterns of ice ages, glacial cycles, and long-term climate change. On the abyssal plain, scattered among the foraminiferal ooze and clay, lie curious objects that look at first glance like dark potatoes. These are polymetallic nodules, mineral concretions that form around tiny nuclei, a shark tooth perhaps, or a fragment of shell, through the extraordinarily slow precipitation of minerals from seawater and the fluids moving through the sediment. Fact number 64. Polymetallic nodules grow at a rate of a few millimeters per million years, one of the slowest known processes of mineral formation, meaning a nodule the size of a tennis ball may be tens of millions of years old. The minerals they contain, manganese, iron, copper, nickel, and cobalt, are commercially valuable, and the nodules are distributed across vast areas of the abyssal plain. Their potential as a mineral resource has attracted considerable interest, and the question of whether and how to extract them, while minimizing ecological damage to the abyssal communities that depend on them, is the subject of active research and international regulation. Scattered across the seafloor in a different pattern are the methane hydrates, structures in which methane molecules are trapped within a lattice of water ice crystals, stable only at the high pressures and low temperatures of the deep sea. They occur in vast quantities on the continental slopes and in the sediment of the abyssal plain, representing one of the largest reserves of carbon on Earth. Fact number 65. Methane hydrates on the ocean floor may contain more carbon than all known coal, oil, and natural gas reserves combined. Stored in the permanent cold and pressure of the deep sea in a form stable only under deep sea conditions. The deep sea floor is also the final destination of much of Earth's organic carbon. Fact number 66. Organic material that reaches the deep sea floor and is buried in sediment is effectively removed from the active carbon cycle, locked away for millions of years in the sediment archive of the abyssal plain. Beneath the sea floor itself, life continues deeper than might be imagined. Deep sea bacteria have been found living in rocks several kilometers below the seafloor, extracting energy from chemical reactions between minerals and water, living in pores and cracks in the rock at temperatures and pressures that push the boundaries of what is thought possible for living organisms. Fact number 67. The total weight of bacteria living in the rocks and sediment below the deep sea floor may be comparable to the total weight of all bacteria living in the surface ocean. The subsurface biosphere is as large as the ocean biosphere. The floor of the deep sea is not a passive surface. It is an active archive, recording the history of the ocean and the atmosphere above it in the chemistry of its sediment layers, accumulating mineral wealth through processes too slow for any human timescale to observe directly, harboring life in its sediment and in the rocks beneath. It is one of the most patient places on Earth, and within that patience, there is sound, not silence, but a deep, rich acoustic world that connects the deep ocean to the surface and to every corner of the globe. That acoustic world is where we are going next. The deep sea is often imagined as silent. It is not. Sound travels through the deep ocean with an efficiency that has no parallel in any terrestrial environment. The medium of seawater, dense, continuous, under pressure, transmits sound approximately 4 times faster than air and with far less energy loss over distance. A sound produced in the deep ocean can travel thousands of kilometers across entire ocean basins before it fades to inaudibility. The deep sea is not silent. It is filled with sound. Fact number 68. Sound travels approximately 1,500 meters per second in seawater, approximately 4 times faster than in air, and loses energy far more slowly, allowing sounds to travel thousands of kilometers through the ocean. The physics of the deep ocean creates a natural acoustic waveguide at a specific depth. Between approximately 600 and 900 meters, the temperature and pressure conditions of the ocean combine to create a layer where sound velocity is at a minimum. Sound waves traveling through the ocean are bent, refracted toward this minimum velocity layer, just as light is bent by a lens. Once a sound enters this layer, it is continuously refracted back toward it as it strays above or below, trapping it and allowing it to propagate enormous distances with minimal loss. This layer is called the soothe channel, the sound fixing and ranging channel. It was discovered during World War II when military researchers noticed that underwater explosions could be detected at remarkable distances, and it was exploited for military purposes before being open to scientific study. Fact number 69. The soothe channel acts as a natural acoustic waveguide, trapping sound energy and allowing it to travel thousands of kilometers through the ocean with far less loss than it would experience outside the channel. The largest animals on Earth have discovered the soothe channel, or rather, their calls have evolved to exploit it. Blue whales produce extraordinarily low-frequency calls, below 20 Hz in some cases, well below the lower limit of human hearing. These infrasonic calls, propagating through the soothe channel, can travel thousands of kilometers. A blue whale calling in the North Atlantic may be heard by another blue whale near Iceland or near the Azores. The ocean is their acoustic environment, and its physical properties allow them to communicate at distances that no terrestrial animal can match. Fact number 70. Blue whale calls traveling through the soothe channel can potentially be detected thousands of kilometers from their source, allowing blue whales to communicate across entire ocean basins in a form of long-distance connection that has no terrestrial equivalent. During the Cold War, the United States Navy built a network of underwater hydrophones called the Sound Surveillance System, or SOSUS, distributed throughout the world's oceans, positioned to exploit the soothe channel for tracking Soviet submarines. Declassified portions of this network were made available to scientists in the 1990s, revealing an acoustic picture of the deep ocean that had never previously been accessible. What the SOSUS recordings revealed was a richly inhabited acoustic environment. Whale calls from populations scientists had not known to exist. The signatures of deep-sea earthquakes detected at distances of thousands of kilometers. Mysterious sounds of unknown origin that have been the subject of scientific investigation ever since. Fact number 71. The SOSUS network, originally built to track submarines, revealed an acoustic world in the deep ocean of extraordinary richness. Whale calls, geological events, and sounds of unknown origin, all detectable across thousands of kilometers of open ocean. The sounds of the deep sea are not only biological. The geological activity of the mid-ocean ridge system produces a constant background of low-frequency sound. The rumble of deep-sea earthquakes, the hiss of volcanic activity, the creak and groan of tectonic plates moving against each other at rates of centimeters per year. These geological sounds travel through the water and through the sea floor, contributing to the acoustic landscape of the deep ocean. Fact number 72. The deep ocean's geological activity. Earthquakes along mid-ocean ridges, hydrothermal activity, and volcanic eruptions on the sea floor produces a constant background of low-frequency sound, detectable throughout the ocean basin. Many deep-sea fish also produce sounds for communication, using their swim bladders as resonating chambers, contracting and relaxing the muscles surrounding the bladder to produce drumming or grunting sounds. Deep-sea fish communicate with each other in the darkness where vision is useless. These sounds travel efficiently through the water, allowing fish to communicate over distances far greater than any visual signal could reach. Fact number 73. Many deep-sea fish produce sounds using their swim bladders for communication. Their calls traveling through the acoustic environment of the deep sea to reach potential mates or rivals at distances that vision in the permanent darkness could never achieve. The crackling of snapping shrimp, familiar from coastal waters but present throughout the deep sea wherever the shrimp occur, adds a continuous, textured background to the deep acoustic environment. Individual snaps merge into a continuous crackling that resembles rain on a tin roof or the crackling of a wood fire. A biological white noise generated by billions of tiny crustaceans closing their specialized claws at speeds that produce cavitation bubbles. Fact number 74. The crackling sound of snapping shrimp is audible throughout much of the world's oceans and represents one of the most consistent biological sounds in the marine acoustic environment. A continuous background produced by billions of individual animals. The deep sea, then, is a world not of silence, but of sound. A richly acoustic environment where geological events and biological communications travel across ocean basins, where the calls of the largest animals on Earth propagate through a natural waveguide discovered by military engineers, where the deep geological activity of the planet is audible as a constant low-frequency background. It is a world where sound connects what darkness separates, where organisms that cannot see each other across thousands of meters of dark water can still hear each other. And this acoustic world, like so much else about the deep sea, turns out to be connected to human life in ways that most people never consider. Those connections are where we are going next. Begin with the climate. The ocean is the primary regulator of Earth's climate. It absorbs heat from the sun and distributes it around the planet. It absorbs carbon dioxide from the atmosphere and stores it in the deep. And the mechanism by which it does both of these things is a deep ocean circulation system that operates primarily well below the surface. Fact number 75. The ocean absorbs approximately 90% of the excess heat trapped by greenhouse gases in the atmosphere. The deep ocean acting as a vast thermal reservoir that moderates the rate at which surface temperatures change. Fact number 76. The ocean stores approximately 50 times more carbon dioxide than the atmosphere, with most of this carbon dissolved in deep water, making the deep ocean a critical component of the global carbon cycle. The moderating influence of the deep ocean circulation on surface climates is something most people experience without knowing it. The climate of northwestern Europe, Britain, Ireland, Norway, the Netherlands, is significantly warmer than equivalent latitudes in North America because of the warm North Atlantic current, which carries heat northward as part of the thermohaline circulation. Without this oceanic heat transport, London would have winters more similar to those of Newfoundland than those it currently experiences. Fact number 77. The deep ocean circulation is responsible for keeping northwestern Europe approximately 10 degrees Celsius warmer than it would otherwise be at its latitude, a climate benefit delivered by the slow movement of water through the deep sea. Now consider what is lying on the deep sea floor between you and anyone you communicate with on another continent. Fact number 78. Approximately 95% of international data traffic, every internet search, video call, financial transaction, and message crossing an ocean, travels through fiber optic cables lying on the deep sea floor. These cables, some no thicker than a garden hose, run along the abyssal plain across every ocean basin, connecting continents in networks that carry the vast majority of global communication. They are protected by armoring in shallow, near-shore areas where damage is more likely. But in the deep sea, they lie simply on the sea floor, in the cold and the darkness, carrying the information that sustains modern civilization. Fact number 79. The first transatlantic telegraph cable was laid on the ocean floor in 1858, the beginning of a network of submarine cables that has grown continuously for more than 160 years into the infrastructure that carries modern global communication. The organisms of the deep sea have also contributed directly to human medicine and biotechnology. When hydrothermal vents were discovered in 1977, scientists found bacteria living in the vent water at temperatures that should have destroyed any biological molecule. These thermophilic bacteria, heat-loving organisms, had evolved enzymes stable at temperatures far above what surface organisms could tolerate. One of these enzymes, a heat-stable DNA polymerase, proved to be the key to one of the most important laboratory techniques in modern biology. Fact number 80. The polymerase chain reaction, PCR, which is fundamental to molecular biology, medical diagnostics, forensic science, and virtually all modern genetic research, depends on a heat-stable enzyme originally derived from a thermophilic organism related to those found at deep-sea hydrothermal vents. Every COVID-19 test, every DNA paternity test, every forensic analysis of a crime scene, every genetic test for hereditary disease, all of these depend on PCR, and PCR depends on an enzyme from an extremophile organism. The deep sea is in the diagnostic laboratory. Fact number 81. Deep sea organisms, particularly sponges, tunicates, and microorganisms, have produced compounds with potential anti-cancer, antiviral, and antibacterial properties that are the subject of active pharmaceutical research. Medical ultrasound imaging, used to image pregnancies, diagnose organ conditions, and guide medical procedures, derives directly from sonar technology originally developed for underwater navigation and exploration. The principles of acoustic imaging in water, developed for deep-sea research and naval applications, became the basis of acoustic imaging in biological tissue. Fact number 82. Medical ultrasound technology is a direct descendant of sonar developed for ocean exploration. The deep sea gave medicine one of its most widely used imaging tools. The study of deep-sea extremophile organisms has also expanded our understanding of where life might exist elsewhere in the solar system. The moons Europa and Enceladus are thought to have subsurface oceans, vast bodies of liquid water beneath their icy surfaces, and those subsurface oceans may have hydrothermal activity on their floors. Fact number 83. The discovery of thriving chemosynthetic communities at Earth's deep-sea hydrothermal vents has directly informed the design of instruments sent to search for life on Europa and Enceladus, demonstrating that life can exist in permanently dark, ice-covered oceans sustained by chemical rather than solar energy. The connections between the deep sea and human life are then far closer than the physical remoteness of the deep ocean suggests. The climate we live in, the communication networks we depend on, the medical tools we use, the scientific technologies that underpin modern research, all of them are touched by the deep sea in ways that most people navigating their daily lives never have cause to consider. And underlying all of these connections is a physical process operating in the deep ocean. A circulation so vast and so slow that its timescale makes human civilization seem brief. That process is where we are going next, somewhere in the North Atlantic, north of Iceland. A body of water is becoming very cold. It has traveled a long way to reach this point. It began, or rather, this particular water began, somewhere in the warm tropical Atlantic, perhaps near the equator, perhaps near the Caribbean. It was carried northward by surface currents, carried as part of a flow that most people know as the Gulf Stream, moving at the surface of the ocean, warmed by the tropical sun, losing heat gradually as it traveled north. And now, in the cold high latitudes of the North Atlantic, it has given up most of that heat to the atmosphere. The water is now cold, just above freezing, and cold water is dense. As this cold, dense water becomes denser than the water around it, something happens that seems simple but has global consequences. It sinks. Fact number 84. The thermohaline circulation, the global deep ocean conveyor belt, is driven by differences in the density of seawater, which are caused by differences in temperature and salinity. Cold, salty water is denser than warm, fresh water, and sinks to the ocean floor, driving a circulation that connects all the world's oceans. The sinking happens in a few specific locations, primarily the Nordic seas near Greenland and Iceland in the North Atlantic, and the Weddell Sea near Antarctica in the Southern Ocean. In these regions, the surface water becomes cold and, through evaporation and through the formation of sea ice, which leaves salt behind in the liquid water, salty enough to sink. Once it sinks, it begins a journey along the ocean floor that will last approximately 1,000 years. Fact number 85. The water currently sinking in the North Atlantic will spend approximately 1,000 years in the deep ocean before it returns to the surface, moving slowly along the ocean floor, through the deep Atlantic, around Antarctica, into the Indian and Pacific Oceans, before eventually upwelling at the surface. As this deep water moves along the ocean floor, it carries with it the dissolved carbon dioxide it absorbed when it was last at the surface. It carries dissolved oxygen. It carries the nutrients released by the decomposition of sinking organic matter. And as it moves, slowly, over decades and centuries, it gradually releases some of these substances and accumulates others, changing character as it travels. The return path of the circulation operates at the surface. As deep water upwells in the Indian and Pacific Oceans, it warms and becomes less dense. It flows back toward the Atlantic at the surface, joining the Gulf Stream and the North Atlantic Current, and ultimately returning to the sinking regions of the North Atlantic to complete the circuit. Fact number 86. The Gulf Stream, the warm surface current that moderates the climate of northwestern Europe, is the return flow of the thermohaline circulation, carrying warm water back toward the North Atlantic sinking regions to replace the cold water that has descended to the deep. The consequences of this circulation for the surface world are profound. The heat carried northward by the Gulf Stream and North Atlantic Current is why London, at a latitude similar to Calgary in Canada, has winters that rarely see sustained freezing temperatures. Without the ocean's heat transport, without the thermohaline circulation delivering warm water to the North Atlantic, northwestern Europe would be dramatically colder. Fact number 87. Without the thermohaline circulation, northwestern Europe would experience temperatures approximately 10 degrees Celsius colder than it currently does. A difference that would transform the climate, agriculture, and habitability of some of the world's most densely populated regions. The thermohaline circulation also plays a critical role in the ocean's ability to absorb carbon dioxide. When surface water sinks to the deep ocean, it carries with it the carbon dioxide it has dissolved from the atmosphere. This carbon is transported to depth and effectively removed from the active carbon cycle for the duration of the water's time in the deep, approximately 1,000 years. The thermohaline circulation is one of the mechanisms by which the ocean stores carbon that would otherwise remain in the atmosphere. Fact number 88. The thermohaline circulation has been operating continuously for millions of years, cycling water between the surface and the deep in a global circuit that distributes heat, nutrients, and dissolved gases around the entire planet. The water currently in the deepest parts of the North Atlantic last saw the surface approximately 1,000 years ago, during what historians call the medieval warm period, when Viking explorers were settling Iceland and Greenland and reaching the shores of North America. That water has been traveling in the dark, in the cold, in the silent deep of the ocean since then, slowly moving southward along the Atlantic floor, carrying a fragment of a medieval ocean with it. Fact number 89. A glass of water from the deep North Atlantic contains molecules that were last at the surface approximately 1,000 years ago. Ancient water by human timescales, still carrying traces of the medieval ocean in its chemical composition. The thermohaline circulation is sometimes called the ocean conveyor belt, a metaphor that captures something of its continuous, unceasing global character. It connects the surface and the deep. It connects the tropics and the poles. It connects the Atlantic, Pacific, Indian, and Southern Oceans into a single circulation system. And it does all of this quietly, invisibly, in the deep sea, at a pace that makes any human activity seem hurried. It has been operating in roughly its current form for millions of years. It will continue long after any human being reading these words has lived their life and returned to the elements. The thermohaline circulation is one of the most important processes on Earth, and we are only beginning to understand it fully, as we are only beginning to understand the deep sea more generally. The extent of what remains unknown and the tools being developed to discover it is where we are going next. More than 80% of the world's oceans remain unexplored and unmapped in detail. This is a sentence worth sitting with, not with anxiety, but with a kind of quiet wonder. The largest environment on Earth, covering more than 2/3 of the planet's surface, remains largely unknown. Most of its floor has never been directly observed. Most of its organisms have never been described. Most of its processes have not been measured over timescales long enough to understand them fully. The deep sea is not a frontier that has been explored and mostly understood. It is a frontier whose exploration has barely begun. Fact number 90. The deep sea floor is less explored than the surface of the moon. More of the lunar surface has been directly imaged at high resolution than the floor of Earth's own oceans. The biological unknown is particularly striking. Based on the rate at which new species are described and the fraction of the deep sea that has been sampled, researchers believe that more than 90% of deep sea species remain undescribed by science. The total number of species in the deep sea is not known. Estimates range from several 100,000 to several million, depending on the assumptions made about unstudied habitats and organism groups. Fact number 91. Approximately 2,000 new deep-sea species are described by science each year. Yet researchers believe this rate of discovery represents only a small fraction of the species that actually exist in the deep ocean. The deep scattering layer, that vast community of mesopelagic organisms that undertakes the nightly diel vertical migration, remains incompletely understood, despite being one of the most ecologically significant communities in the ocean. Its total biomass, how many organisms are in the mesopelagic zone globally, is not known with certainty. Estimates have varied by orders of magnitude, and recent research using new acoustic and net sampling methods suggests that the mesopelagic zone may contain far more biomass than previously thought. Fact number 92. The total biomass of organisms in the mesopelagic zone, the twilight zone between 200 and 1,000 meters, is not known with certainty and may have been significantly underestimated by previous surveys. New tools are transforming the exploration of the deep sea. Autonomous underwater vehicles, AUVs, can operate without a connection to a surface ship, navigate independently, descend to great depths, and survey large areas more efficiently than any crewed submersible. They can stay at depth for hours or days, covering terrain that would require many crewed dives to survey. As their battery technology, navigation systems, and sensor arrays improve, they are becoming the primary workhorses of deep-sea exploration. Fact number 93. Autonomous underwater vehicles capable of reaching hadal depths have expanded the range of environments that can be routinely surveyed, allowing exploration of the deepest trenches without the engineering complexity and risk of crewed vehicles. Environmental DNA sampling, sometimes called eDNA, represents a different approach to understanding deep-sea biodiversity. Rather than attempting to capture or directly observe organisms, eDNA sampling involves filtering deep seawater through fine membranes and then sequencing the genetic material left behind by organisms that have passed through. Every organism sheds cells, mucus, feces, and other biological materials containing DNA. By sequencing the DNA in a water sample, scientists can detect which organisms are present in an area without ever seeing them. Fact number 94. Environmental DNA sampling of deep sea water can detect the presence of organisms, including rare or elusive species, from the genetic traces they leave in the water, without requiring physical capture or direct observation. Deep-sea genomics, the large-scale sequencing of DNA from deep-sea organisms and environmental samples, has already revealed entirely new branches of the tree of life. In the deep-sea sediment and in the water of the Hadal zone, genetic sequences have been found that do not match any known organism. Evidence of entirely unknown groups of bacteria, archaea, and possibly other microorganisms whose biology remains to be understood. Fact number 95. Deep-sea genomic surveys have discovered genetic sequences from entirely unknown branches of the tree of life, organisms whose existence was unknown before their DNA was found in deep-sea sediment. Long-term monitoring stations on the deep-sea floor are being established at key locations to track changes in deep-sea temperature, chemistry, and biology over periods of years to decades. The deep sea has historically been studied through short snapshots, a submersible dive, a dredge haul, a sediment core, rather than through sustained observation over time. These monitoring stations represent a shift toward understanding the deep sea as a dynamic system that changes over time, not merely a stable background. Fact number 96. Long-term monitoring stations on the deep sea floor are beginning to reveal that the deep ocean is not as static as once assumed. Temperature, chemistry, and biological activity all change over time in response to conditions at the surface. The study of the deep sea also increasingly informs the search for life beyond Earth. The moons Europa and Enceladus, orbiting Jupiter and Saturn respectively, are thought to harbor vast liquid water oceans beneath their icy surfaces, possibly with hydrothermal activity on their ocean floors. The demonstration that chemosynthetic life can thrive at hydrothermal vents on Earth has transformed scientific thinking about the possibility of life in these subsurface oceans. Fact number 97. Instruments designed to search for life on Europa and Enceladus draw directly on the technology and biological understanding developed through the study of deep-sea hydrothermal vent communities. The deep sea as a guide to what might be possible on ocean worlds elsewhere in the solar system. Fact number 98. Approximately 2,000 new deep-sea species are discovered and described each year, a rate that suggests the deep ocean will continue yielding biological surprises for generations of scientists to come. The deep sea, then, is a frontier in the truest sense, not merely unexplored, but actively yielding new discoveries as the tools to explore it improve. Every new submersible dive, every eDNA survey, every sediment core, every baited camera lowered to the Hadal floor adds to a picture of extraordinary complexity and richness that is still far from complete. Fact number 99. Scientists estimate that if the current rate of deep-sea species discovery continues, it will take more than a century to describe even the known species of the deep sea. The biological exploration of the deep ocean is a multi-generational scientific project, and the 100 facts that have carried us through tonight's journey are themselves only a small window into a world of such scale and richness that 100 facts cannot begin to contain it. What they can do, perhaps, is leave us with a sense of something worth carrying into the quiet of the night, a sense of the extraordinary depth and patience and age of the world beneath the waves. That is where we are going. In our final section, there is nothing left to explain. The zones have been described: the twilight mesopelagic, the midnight bath hypelagic, the abyssal plains, the Hadal trenches. The history of exploration has been traced from the Azoic hypothesis to the HMS Challenger, to the bathysphere, to the Trieste, to the discovery of hydrothermal vents, to the ongoing pace of discovery. The marine snow has been described, falling now through thousands of meters of dark water as you listen, as it has been falling without interruption for hundreds of millions of years. The bioluminescence has been described, the living light of the midnight zone, flashing and glowing in permanent darkness, seen by no human eye tonight. The creatures have been visited. The giant squid with its dinner plate eyes, the Greenland shark moving slowly through Arctic water for 4 centuries, the octopus that tended her eggs for 53 months in the cold dark of a seamount. The hydrothermal vents have been visited, and the cold seeps and the whale falls and the underwater brine lakes. The sediment cores and polymetallic nodules and methane hydrates of the deep sea floor have been described, and the acoustic world carried by the SOFAR channel, and the connections between the deep sea and everyday human life, and the thermohaline circulation moving water that last saw the surface 1,000 years ago. All of that is there now, somewhere in the mind, held gently, without urgency. What remains is simply to rest in it. Fact number 100. The deep sea has existed in roughly its current form for tens of millions of years. One of the most ancient and stable environments on the surface of the Earth, carrying on its slow business of darkness and pressure and biological chemistry with a patience that makes human civilization seem momentary. Right now, as you rest, marine snow is falling. Tiny particles of organic material, fragments of dead phytoplankton, fecal pellets, shed mucus, are drifting downward through thousands of meters of dark water in every ocean on Earth. They are falling slowly, so slowly that a particle leaving the surface now will not reach the abyssal plain for weeks or months. They are falling in the Atlantic and the Pacific and the Indian Ocean and the Southern Ocean and the Arctic. They have been falling without interruption since before the first animal with bones existed. They will continue falling when all the bones of all the animals that have ever lived have long since become part of the sediment below. The marine snow is falling now. In the permanent darkness of the midnight zone, 1,000 to 4,000 meters below the surface of every ocean, organisms are producing light. A siphonophore 40 meters long is drifting through the dark water, its colonial body producing a faint bioluminescent glow along its entire length. A dragonfish is scanning the water with its invisible red light. An anglerfish dangles its bioluminescent lure in the darkness and waits. These displays are happening right now, in the absolute blackness of the deep sea, seen by no human observer, carrying on as they have carried on for hundreds of millions of years, in a world that has never needed human observation to sustain its extraordinary activities. The bioluminescence is flashing now. Somewhere in the North Atlantic, water that last saw sunlight approximately 1,000 years ago is moving slowly southward along the ocean floor, carrying the dissolved gases and nutrients of a medieval sea toward the Southern Ocean, and eventually toward the upwelling regions of the Pacific, where it will finally rise to the surface and see light again. That water, was at the surface when Viking explorers were charting the North Atlantic, when the great cathedrals of Europe were being constructed, when the patterns of civilization we now inhabit were being laid down by people who had no concept of the ocean conveyor, or the thermohaline circulation, or the deep-sea ecosystem their world sat upon. The thermohaline circulation is moving now. In the cold, dark water of the Hadal Zone, in the deepest trenches of the 5 oceans, Hadal amphipods are moving across the sea floor, their small bodies adapted to pressures that would crush any surface organism, living their extraordinary lives in conditions that no human technology could easily create or maintain. A snailfish is drifting through the water column of a trench, its gelatinous body perfectly adapted to the crushing pressure, as unconcerned by the darkness and the cold as a bird is unconcerned by the openness of the sky. These organisms are living now in the most extreme accessible environment on Earth, going about the business of their extraordinary lives with the same patient competence that their ancestors have shown for millions of years. The Hadal life is living now. On the abyssal plane, a deep-sea coral is adding a fraction of a millimeter to its skeleton. It has been doing this for 4,000 years. The skeleton it has built in that time records, in its growth rings, the temperature and chemistry of the water in every one of those 4,000 years. A library of ocean history written in calcium carbonate and tended by an animal no more remarkable in appearance than a piece of branching ivory. 4,000 years of patient, slow, continuous growth in the cold and the dark. The coral is growing now. The deep sea surrounds us without most of us ever thinking of it. The fiber optic cables carrying the data that makes modern life possible lie on its floor. The thermohaline circulation moderating our climate operates within it. The carbon cycle that regulates the composition of the atmosphere depends on it. The medicines derived from its organisms circulate in our bodies. The enzymes from its extremophiles operate in our laboratories. And in the darkness below, in a world most of us will never visit, that very few humans have seen directly, that science is only beginning to understand, the ancient processes continue. Marine snow falls, bioluminescence flickers, ancient water moves slowly along ancient paths. A coral grows its fraction of a millimeter. It has been doing this for a very long time. It will continue long after tonight is over. Sleep well.